Hi, this is what you'll probably look at as the first of a few quick videos where I'm just listing out prerequisites you should have for the math methods class you're about to take, the course we call Physics 306 here. And this one is about things in basic 1D calculus. Again, I'm creating this for a particular course, very standard course of the physics curriculum called Math Methods in Physics, or something similar everywhere. On my campus, Cal State Dominguez Hills, it's Physics 306. This video and a couple of others that accompany it are meant to just flip through some of the material that I expect you to know before this course, and I'll mention when some things are within prerequisites, but I'll cover more of them. I may actually cover more than you expect of review because, sometimes you want to go back and make sure everyone has everything fully. But even if I don't cover something that was covered in your first semesters of math and physics, calculus and physics, you are responsible for it, even if I don't explicitly do it. And my disclaimer is that this is not meant to be at all an exhaustive list of material that I expect you to know. In fact, there are whole groups of topics that I don't touch in these videos that I do expect you to know. The simplest statement about 1D calculus is, you've had 3 semesters of calculus and of physics, and I expect you to know all of it. But all joking aside, it starts with the definition of derivative. In fact, it starts before that with discussions of continuity and things. But in physics, we kind of jump in further on. We also hit very early in physics integrals as what we call antiderivatives, undoing the process, and integrals as area under curves. Those things are actually related in calculus by some things called fundamental theorems of calculus. Useful to know those. We won't deal in theorems as much, but they're good to know. I have a note on that later. Just for review of what I personally expect, in my first semester physics class, I give this kind of crib sheet on calculus, because I know we get ahead of calculus, where I toss all these things out there. And those are all from first semester calculus, and a lot of them are used in first semester physics. So you should be fully familiar with those and comfortable with applying those and a lot more things. I actually give more sheets in that class, but I wanted to toss out the basics first. That said, even once you get through all that, some problems are still non-trivial. I bet you can't do these in your head, but I bet you could if you sat down long enough. There's a derivative. Now, everything in this derivative is approachable with stuff I had on the crib sheet on the previous slide. So you could actually do it. You just need to sit down and work through it. This integral, and I didn't show any crib sheet on integrals yet, but you have all the tools to solve this integral. Note, it's a definite integral. You should know what that means. You're going to get a number out. And you probably can't do this right away. You can't do it in your head, I'm pretty sure, unless you know some things beyond what are the prerequisites for this course. But you do have the tools to do that. And by the way, you generally would integrate by parts twice to get that integral. Some problems, in principle, you have the tools to do, but they're actually still hard. If I gave you this, unless, again, you've had things that go a little beyond what I'm expecting for prerequisites, you might not even know where to start. I will show you how to approach this at some point. But the square root in there, along with the exponential function separately, could really throw you, and you might not know what to do. So I do recognize that problems can still be hard, even though you, in principle, have all the tools. So we will go through some of that, how you apply those tools to solve harder problems. Just since I'm listing things, I want to say, you should know higher derivatives, the second derivative, third derivative, know what they are. You already know we do that. We did that in first semester physics. We took the second derivatives, In fact, we had applications. You should know not only the applications you see first in math, which are derivatives for finding maxima and minima. Collectively, we say extrema. You should know the physics application, what a time derivative means in simple motion. That is just the first time derivative is the velocity, and the second time derivative is the acceleration. You should know a lot more than that, but those are examples of what you should know. A little note about definitions. I said at the beginning it starts with the definition of derivative, and you haven't seen me bring it back yet. You don't remember running into it much in physics probably, but knowing those definitions and theorems, things like the fundamental theorems of calculus, is still useful in physics. To me, the best way to think of that is when we did examples in second semester physics in our order of physics, we did electrostatics with Gauss's law. And we actually broke integrals up into separate parts of a closed surface and made very simple pieces where what was in principle a relatively complicated calculation turned into really simple arithmetic for most of it, even though you were doing calculus. One of my favorite quotes from myself is, one of the best things for a physicist to know about calculus is how to not do it. I'll probably say that several times in the semester, and I'll give you very specific examples, particularly with Gauss's law, as we go through the semester of what I mean by that. But it has to do with really understanding the definitions of derivatives and integrals. But derivatives and integrals aren't the only things you did in freshman calculus. You also dealt with infinite series. We do a lot, and you'll do that more and more as you go to higher physics courses. We often, maybe too much, don't talk so much about convergence, but you should know what Taylor series are, Maclaurin series, which, if you forget, are just Taylor series about x equals 0 or t equals 0. You should have heard of other series, how these are related to the derivatives. There are a few particular series we run into often in physics, and we will expect you to recognize them. Now here, I'm not talking just about prerequisites, but things in the future that we will cover. So we'll talk more about some different series. Actually, we often in physics care most about the value to which a series converges, so I'll spend some time on that for some particular series. One other thing about series that you certainly should have seen but may not have done enough with is the idea of Fourier series. You should have seen these in your physics class, at least conceptually, when we talked about waves, because Fourier series are all about sine and cosine curves and how you use a sum of sine and cosine curves to get other periodic functions. Hopefully in math you did a little bit with that. In physics you may or may not have done much, but you should have heard about it. We will spend a fair amount of time on this course with that. So if you know a little bit about it, it's a good idea to review, because this will be an important topic for us. We'll talk about not just the Fourier series, but extensions of them in a couple different ways, and other related topics. So that's actually a big part of this course, and going to be a bigger part this year than it has been in the past. All that said, I know that there are a lot of really, really good tools online for checking, face the facts, really doing a lot of the relevant calculations. I will talk to you a lot about such tools. My favorite is one called Wolfram Alpha. If you're in this class, and you'll have the PDF of this file as well as being able to see the video, that's an active link to the web page Wolfram Alpha, which will actually help you solve complicated integrals, derivatives, other math, statistical calculations. Even you can do linear algebra through a web interface. In class, I will do examples with that early and later in the class because I think it's an important tool. But you got to remember, no matter how good the tool is, it can't figure out what you wanted to do. It doesn't know, what the question was that was written down. It has to take input from you. And, if it takes the input and thinks it means something else, unless you know how to do these things, you're not going to know if it's doing the right thing. So having these tools is great, and it helps a lot, and it could do the integrals I just tossed out there relatively quickly. But unless you knew how to ask it and you were sure that it was doing what you wanted, it would be useless to you. Again, I'll go through that in class. I'll do a lot of the things I said here in class, but you're responsible for all of the calculus in your previous classes. That said, see you in class.